So 3.1, 3.2 systems of equations. I missed Sam and Paul just walked in, right?
Yeah.
Nobody else. Okay. So systems of equations are just, in our case, we're just going to do pairs of equations, so two equations that we're going to solve simultaneously. You can do larger systems, so you can do like 3 equations, 4 equations, 5 equations. The more equations you have, the more variables you can solve for. But in our case, we're just going to do systems of 2 equations. And the solution to a system is just an ordered pair, which is a solution to both equations. So a solution to a system of equations is an ordered pair that makes both equations true. If you came in a little late, just be sure to grab the homework calendar from me on your way out, so you have that. So the simplest example is see, x equals 5. What's the graph of that equation look like? It's a vertical line, right? So 2, 3, 4, 5. It's this line right here. And then what's the equation of that line look like?
Horizontal.
It's a horizontal line, good. So right here. And so when we graph an equation, remember that every point on that blue line is a solution to the first equation, and every point on the purple line is a solution to the second equation. And so a solution to both equations is going to be a point that's on both lines. So that point of intersection, which is, in this case, right here. And like I said, this is like the simplest example because the system like basically tells you what the solution is. It's the one point where x is equal to 5 and y is equal to 2. Right? So the point 5, 2 makes both of those equations true. This is like the simplest example because we just have a vertical and a horizontal line. But in general, the same is true. If we have 2 lines that intersect, the point where they intersect is a solution to both equations because every point on each line is a solution to its respective equation. And so this on a graph, the point of intersection is the solution to the system. And it turns out that graphing, so finding the solution by graphing, isn't necessarily the most practical thing to do because as soon as we have a system whose solution is not like perfect integer points like 2, 5, you know, like if there's any decimals or fractions involved, it becomes pretty hard to see the solution on a graph and to pick out that point exactly. However, it does help us to see the different types of solutions we can get with systems, and so we'll use graphs to classify systems, or at least to see what classifications we have, and then we'll talk more about how to solve these guys algebraically when it's not practical to use a graph to solve them. So there are 3 different types of solutions, or systems rather. And we'll just look at an example of each. So let's solve we'll do x plus y equals 5 and 2x minus y equals negative 2. So when it comes to graphing, we've been looking a lot at graphing using the slope and y-intercept. I wanted to point out that you don't have to use the slope and y-intercept to graph, so you don't have to put these in slope-intercept form in order to graph. One really quick way to graph an equation, if you have both variables on one side, is to just use the intercepts. So if x was 0, notice that this term would just go away, and that tells me that y is 5. And so my x or my y-intercept is just 0, 5. Which 1, 2, 3, 4, 5 is right here. And then if y is 0, again, that term just goes away and we get x equals 5. And so my x-intercept is 5, 0. And then I have 2 points on my graph, and I can draw the graph without having to do a whole bunch of algebraic manipulation to put it in slope-intercept form. So my first line is right here. And then we can do the same thing with the other one, because again, we have both our x's and y's on the same side. So if x was 0, that would make this term 0, so I have negative y equals negative 2. So y equals positive 2. So that's the point 0, 2. And if y is 0, then I have 2x equals negative 2, and so x is negative 1. So that's this point right here. And so now we can draw our line. As soon as you have 2 points on a graph, you can draw your line. So notice we just graph these lines exactly the same way as we've been doing. So we're graphing 2 separate lines that have nothing to do with one another, and then to solve this system, we're just looking at where they intersect. So there's nothing new about graphing systems as opposed to graphing individual lines. We're just doing 2 on the same axis as opposed to just graphing 1. So this type of system is what we call independent. So this system, I guess I should do it in the order they do it in my math lab, is consistent. What consistent means is that the system has a solution, or more than one solution. So when we call a system consistent, it just means that some solution exists. So it has solutions. And then in this case, it is also independent. Which means we have 2 lines. It is possible to have a dependent system where both equations represent the same line, so you just end up with 1 line. So when we have a consistent system, which is independent, that means we have 2 separate lines that intersect somewhere. And that results in having 1 solution. So both of these things together tell us that we have exactly 1 solution, which in this case is 4, 1. That point of intersection. It would be 1-4. I'm sorry. My last class I did a different system and it was 4-1. It's inconvenient. Thank you. Yes?
What if there was a curve?
So we're just doing linear ones, but you're right. So if we had a consistent independent system of nonlinear equations, there could be more than one solution. So you can end up with 2 solutions, 3 solutions. We're just going to focus on linear systems, so we'll only get one infinite or none. But if you have a nonlinear system, yes, one of those could turn around and cross the other one again. So our second possibility we're going to solve x plus y equals 5 and y equals 5 minus x. So to graph that first one, again, if I put 0 in for x, I get y equals 5. 1, 2, 3, 4, 5. If I put 0 in for y, I get x equals 5. So my first equation, the line is right there. And then that second one, well, that one's in slope-intercept form. So we have a y-intercept at 0, 5. And then our slope is -1. So if we move to the right one, we go down 1. Which gets me a point right here, and it turns out we end up with exactly the same line, right? And you can kind of see too, like if you manipulate the equations, they'll end up being the same equation as well, right? If we subtracted x from both sides of that first equation, we would just get y equals 5 minus x, which is the same equation. And so, does this system have solutions? Are there any points that are on both of those lines? Yeah, all the points are on both of those lines, right? So it is consistent. Because it has solutions. But then this one is dependent because both lines are the same, right? I don't have 2 separate lines like I did the last time. So we call this dependent. Which just means that both equations represent the same line. And so those two together give me infinitely many solutions. So we have to be a little bit careful when saying that we have infinitely many solutions. When we were solving equations with one variable, remember that when we got an identity, so something that was always true, we said all real numbers were solutions. We can't say the same thing here because it's not true that every single point is a solution to this system, right? If I pick a point like right here, that's not a solution to the system, right? The reason there are infinitely many solutions is that there's infinitely many points on that line. So what we mean when we say infinitely many solutions is that if it's a solution to one of the equations, it is also a solution to the other. And that's why we call it dependent, right? So whether or not it's a solution to one equation depends on if it's a solution to the other. So be sure that you say infinitely many solutions here as opposed to like all real numbers, because it's not true that every single point is a solution. Does that make sense? We're a little tired this morning after taking a test last night. I hear you. Okay, so we have one more possibility. So let's do f of x equals 2x minus 4 and g of x equals 2x plus 1. So remember that the y coordinate is just the output of the function, right? So this is really exactly the same as the system y equals 2x minus 4 and y equals 2x plus 1. So we'll graph exactly the same way. Both of these are in slope-intercept form. Oh, I meant to make one of them a different color so we can see the difference. So that first one, we have a y-intercept at 0, -4. So 1, 2, 3, 4 is down there. And then we have a slope of 2, which means moving to the right 1 will increase our y value by 2. So that gets me a second point right here. And oh, that's not right. There we go. There's my line. And then that second one, we've got a y-intercept at 0, 1. So that's this point right here. And again, my slope is 2, so moving to the right 1 unit will increase my y value 2 units. So that gets me a second point here. And there's my second line. And what do you notice about these guys? They're parallel, right? Which we could have figured out just by looking at the equations as well, right? Because they have the same slope. So two lines with the same slope but different y-intercepts are parallel lines, which means they never intersect. So what does that tell me about my solutions? There aren't any solutions, right? So this is, we call this system, so it is inconsistent. Right, because if consistent means that solutions exist, and if there's no solutions, then it's going to be inconsistent. So there are no solutions. Is it dependent or independent?
Independent.
It's independent, right? And in fact, it's impossible to have an inconsistent system which is dependent, because remember that dependent means they're the same line. And if they're the same line, then you can't have no solutions, right? So, however, so I don't usually even say that they're independent as well, but in my math lab, it makes you check both boxes. So we'll just write it. So it's impossible to have an inconsistent system that is dependent, but for my math lab's sake, we will also call it independent, even though it's redundant, which just means we have two different lines. And so this system has no solution. So these two together tell me that I have no solution. So there's sort of two things we can do with systems. We can classify them, which is just saying if they're consistent slash inconsistent and dependent slash independent. And then we can solve them, which is finding the solutions. So if you're asked to solve, you will either say there is a solution and give what the solution is, there are infinitely many solutions, or there is no solution. If you're asked to classify, you're just checking the boxes. And really, you guys will just do that in my math lab tonight and then like never do it again. Well, probably until later other classes where you're asked to classify other types of systems. But for the most part, we're just going to be looking for the solutions. And like I said, it's really nice to graph these guys to kind of see what it looks like to have no solution, a solution, or two of the same line, or the same line. But it's sort of impractical to solve by graphing as soon as we get into less simple equations, right? So if I have a line like this and a line like it's like too close, like that, like what is the point of intersection, right? Like it's like 3 point something, right? Like, is it 3.3? Is it 3.25? Is it 3.31792? Right? So, like, finding this x value right here is kind of difficult if they don't cross at integer points, right? So it becomes sort of impractical to solve by graphing. So we need an algebraic way to solve these guys. And we actually have two algebraic methods for solving. The one that we will use most often is called substitution. So solving systems by substitution. We're just going to do an example. This is one of those things where I could write like a big, huge, long list of like steps to do it, but it's probably more confusing to write a big, long list of steps to do it than to just like see it a couple times. So we'll do this one first. So let's solve x plus y equals 4. And x equals y plus 1. So notice that second equation tells me that x and y plus 1 have the same value, right? That's what that equal sign means. It means that x and y plus 1 will always have the same value, which means that anywhere I see an x, I can put a y plus 1. I can use them interchangeably, because they're equivalent to one another. So what I'm going to do is in the other equation, and it has to be in the other equation, you can't substitute something in an equation into itself. So in the first equation, I'm going to replace x with y plus 1. So we have y plus 1 plus y equals 4. And in this case, I didn't really need those parentheses because I didn't have anything to distribute, but it's a good habit to get into because when you do need them, if you don't write them, then you're in trouble. So now notice that we have an equation that just has one variable in it, and we know how to solve equations with one variable. So I'm going to combine like terms. And then solve. So I get 2y equals 3 and y equals 3/2. So I just found the y coordinate of my solution. And now I just need to find the x coordinate. But it's pretty handy because this equation, again, tells me that x is equal to y plus 1. So we're going back into that first equation. And we get x equals 3/2 plus 1, which is 5/2. So we sort of do two substitutions here. We substitute for x in the first equation, solve for y, and then substitute back in for y in that second equation. So my solution is the point 5/2, 3/2. Does that make sense what we did there? Where we got everything? Okay, let's do a few more. Sorry, was anybody still writing? Okay. Okay. So this one's not set up quite as nicely because I don't have an equation that says x equals or y equals, right? So in the last one of our equations told us what one of the variables was equal to. However, if you look for variables with a coefficient of 1, they're pretty easy to solve for, right? So I can take that first equation and solve it for y just by subtracting 2x from both sides. And it doesn't matter which equation you solve or which variable you solve for. So you're picking one of your equations and solving for one of your variables. Make your life easy and look for the variable that has a coefficient of 1, because then you don't have to divide by anything to solve, so you don't end up with a bunch of fractions, right? Like if I looked at that second equation and decided to like solve it for x, I would have to go like 3x equals 4 minus 4y and end up with like x equals 4/3 minus 4/3 y, and that seems like kind of a pain in the butt to substitute back into another equation. And so we're trying to make our life as easy as possible, and so we look for that that variable that has a coefficient of 1 because it's easiest to solve for. So we're now we know that y is equal to 6 minus 2x. And so in my second equation, anywhere I see a y, I can replace it with 6 minus 2x. So we have 3x plus 4, replacing our y with 6 minus 2x equals 4. And then again, we've created an equation that has just one variable in it. So we're going to solve for x. So 24 minus 8x equals 4. Combine like terms. -5 equals -20. And x equals 4. And now to find y, we'll go right back into our first equation again, and we have y equals 6 minus 2 times 4. So y equals -2. So our solution is going to be 4, -2. On these guys, a little bit of organization goes a long way as far as like kind of keeping track of everything that's going on. If it's all over the, like if you have steps over here and over here and over here and over here, it's a little hard sometimes to keep track of which equation you already used. So we solved the first equation for y, plug that into the second equation, solve for x, and then went back into the first equation to get our y value. Questions on the process or where anything came from? Does this make sense? Okay, let's give you guys one to try. So let's solve okay, solve that guy. I know that when we are graphing, we like to solve for y a lot because it puts it in slope-intercept form. But do yourself a favor and solve for the variable that has a coefficient of 1. Instead of always solving for y, it'll really make your life easier because you end up not getting fractions. So if we solve for x here, we don't get a bunch of fractions to have to plug in and deal with. So It's not that it's wrong to do it another way, so you can solve either one of the equations for either one of the variables, but if you can make your life easier, it's always a nice idea to do it. So we get x equals 3 plus 2y, and then we'll plug this back in, so we have negative 4, 3 plus 2y, plus 8y equals 7. So distributing gives me negative 12 minus 8y plus 8y equals 7. And another thing I noticed a little bit on your assignments as well is you want to make sure that you always simplify both sides of an equation before you start like doing things to either side, right? Like, so don't add 12 to both sides until you combine like terms on the left. So negative 8y plus 8y is what? It's 0, right? It's not y because y would be 1y, which we don't get, right? We get 0y, and 0 times y is 0. So we get negative 12 equals 7, which tells us what? That we have no solution, right? So just like when we were solving equations in one variable, if we end up with a statement that is never true, then we have no solution. If we end up with a statement that is always true, then we have an infinite number of solutions. So in this case, we have no solution to our system. So then there's one other type of system. I mean, it's really not any different, but it looks a little bit different, so it's worth talking about. It is a problem like this. So let's see. So find the point where the graphs of f of x equals and g of x is 4x minus 5 intersect. So here we're just given two lines in function notation. Remember that the output of each function is like just our y value, right? So what we're really saying is we have y equals negative 3x plus 5 and y equals 4x minus 5. So if we want both of those to be true, we can just make the y's equal to each other, right? So y is both equal to negative 3x plus 5 and also 4x minus 5. And so we're going to just set the outputs equal to each other. So we can say negative 3x plus 5 equals 4x minus 5. Right? Because this is the output of one function, this is the output of the other function, and I want the outputs to be the same. And so it actually turns out that when they're in function notation, it's kind of even simpler than the other case, right? We're just setting the two functions equal to each other and solving for x. So we get, let's see, negative 7x plus 5 equals negative 5, so negative 7x equals negative 10, so x equals 10/7. And then to find our y coordinate, we're just going to plug that input into one of our functions. Doesn't matter which. We'll do g of 10/7. So 4 times 10/7 minus 5 hopefully you guys are getting comfortable using the fraction buttons on your calculator. If you're not sure how to use the fraction buttons on your calculator, feel free to come see me and I can show you. But I'd rather, especially on tests and stuff, I'd rather you not spend a whole bunch of time having to do a whole bunch of fraction calculations when you can just have your calculator do it for you. So this ends up being what, like 40 minus 35, so like 5/7. And so our solution our x value is 10/7, and then our y value is 5/7. Does that make sense? Not too bad. I mean, I could do more, but you guys seem to have the hang of it. Yeah? Feel good? Any questions? Okay. So tonight you just have my math lab, and just these same types of problems. So you'll do some classifying and then some solving. And then tomorrow we'll talk applications. Have a great Tuesday. See you guys tomorrow. It is Tuesday. Yeah, it's Tuesday.